In this video, we introduce three-dimensional objects and we calculate how much we can stuff inside of them, called volume, and how much it would take to actually paint around the surface or to wrap something around the surface, known as surface area. Let's get started. So to begin, I want to introduce the idea of a prism. So when we're talking about a prism, we're talking about something where the base and the top part of your three-dimensional surface are identical, and then there's a height in between them. When you have a prism, to calculate the volume, there's a very simple formula that you'll want to make sure you understand and how to use. And that is capital B, where the capital B here means the area of your base, that's your capital B, times the actual height of the prism. Okay? So for example, we can look at a rectangular prism, which would just be a prism that has a rectangular base at the bottom and the top. So if you have a rectangular prism and you wanted to calculate the volume, how much you can stuff inside of this box, let's say, or this rectangular space, it could be a swimming pool full of water, right? Well, what you would want to do is calculate the area of the base, which in this case is a rectangle. And remember that the area of a rectangle is just the length times the width. So this part right here, L times W in the formula, L times W, that replaces the area of your base, right? So the L times W, length times width, is the area of my base, and then I just need to multiply by its height since it's a rectangular prism, the same surface on the top and the bottom. So now we'd multiply that times the height, and we would have our entire volume. So the volume here is length times width, that's the area of your base, and then multiply that by the height of the prism itself, or LWH. So rather than memorizing brand new formulas for every prism, when you're talking about volume, if you can figure out what the base is, and it's the same base on the top and the bottom since it's a prism, then you simply have to get that area and multiply it times its height. Now what about if you're trying to calculate not how much you can stuff inside of a prism, like a rectangular prism, but rather how much material, whether it be paint, wrapping paper, right? How much material is necessary to cover a three-dimensional prism in this case? Well, that one is simply going to be found by multiplying the area of each side and adding up those areas together. So for example, if we take a look at the base of the bottom here, the area of the bottom was just length times width, but notice that's also the same as on the top, length times width. So if you have two of them, you really have two copies of length times width. And then let me erase that so we can take a look at the other pieces here to consider. So those are the bottom and the top. Let's take a look at another surface here that's important. How about the sides, right? This side, this side. So how much coverage is required for those two sides of your rectangular prism? Well, you would want to take its base times its height for area, right? So the width W there and the height H. So WH, and it happens again, WH in this place. So that's how we could calculate these sides, how much coverage is required there. So you add that up with what we already had, and now you have two copies of WH. And then finally, there's one more piece to consider, right? We've talked about the bottom and the top, the left and the right, and now we could talk about maybe the front and the back. So the front would be here, let's say. How do we calculate that area for this rectangle again? Its base is the L, and its width is the H. So L times H. And notice the front is the same as the back for a prism, right? So that's also going to be this side and the back there. So we have two copies of LH. So if you think of that through for the formula, if you will, if you're memorizing a new formula here for the surface area of covering a rectangular prism, you simply notice, I hope, that there is a 2 in common for all three pieces, all three products. In other words, you could factor out, if you remember from algebra, the greatest common factor. Bringing the 2 in front, you just have twice the sum of WH, LW, and LH. The order doesn't matter, right? In fact, let's go ahead and see how we could apply that in our example below here. It says, find the surface area of a rectangular solid. Now notice here it says rectangular solid, rectangular prism. Those words are typically interchangeable when you're talking about rectangular solids and rectangular prisms, okay? Whose dimensions are 2 feet by 3 feet by 4 feet. So how would we begin? Well, maybe you could draw a picture of a rectangular solid or rectangular prism. Try to draw it better than your professor here. That's pretty rough, okay? But the basic idea is you have 4 rectangular pieces connecting here 1, 2, 3, 4, and then one on the top and one on the bottom, so 6 rectangular pieces all together. So how would we calculate the surface area? Well, we talk about the dimensions, right? Our length is 2, our width is 3, and our height is 4. If you just wanted to calculate your volume, how much you can stuff inside, whether that is cubic feet, cubic inches, it's going to be a cubic unit, you would multiply the area of the base, L times W, times the height, so LWH. In other words, 2 times 3 times 4 would give you your cubic dimensions for the volume. But if you want to know how much would be required to cover the surface of this rectangular solid, you would need to calculate the area of the top and the bottom face, the side faces, and the front and the back faces. So in this case, that would be surface area would be 2 copies of the length times the width, plus 2 copies of the width times the height, plus 2 copies of the length times the height. And again, the order doesn't matter, okay? So if you do that, 2 copies of each of them, you could have also just done 2 times length times width, plus width times height, plus length times height. That's a preference. So if you prefer to multiply 2 at the very end and work with bigger numbers at the end, that's definitely an option. So what is the length times the width here? Well, that would be 2 times 3, or 6, square units, right? Feet times feet is square feet. What is width times height here? 3 times 4, which is, oops, I think I switched screens on you here. There we go. 3 times 4, which is 12, that's right. And then what is the length times the height? 2 times 4, or 8? Very nice. So when you add those together, what do you get? 26 times 2, right? In other words, did you get 52 square feet? If you did, you were correct. So that would be the amount, let's say, of paint. You're going to need to cover 52 square feet of paint, and then you would go to the paint supply store and say, I need to cover this much surface. How many gallons of paint do I need then? And it'll help you make those comparisons and buy the right amount of product. Okay, so when you're talking about surface area for rectangular prisms, all we did again was find the area of each side. That's it, add them together, or you can follow the formula. What about, let's take a look above here at the screen. What about when we're talking about not a rectangular prism, but rather a sphere, kind of like a ball of some type. Maybe you're talking about a basketball or a soccer ball, or even a globe, okay? So when you're talking about a sphere, how would you find the surface area, so the amount to cover the ball, let's say. If you're making a basketball, how much rubber do you need, right, to cover around that ball? Or if you're finding the volume, you're talking about how much space can fit inside the ball. Maybe it's helium if it's a big balloon, a spherical balloon, or maybe you're talking about a basketball and you're blowing it up, that kind of thing. So that would be volume. Well, these formulas are not as obvious to our students typically, but they come from the idea, again, of analyzing the situation. So if you actually took apart the basketball, if you will, and you looked at the rubber that was used in order to enclose the spherical shape, you would find out that the area required for that spherical basketball to be covered would actually incorporate 4 circles. And we know that the area of each circle was pi times the radius of the circle squared. Pi r squared 4 times gives me my formula, 4 pi r squared. So rather than proving it to you, you're going to have to take my word for it today. But that is what you'd actually discover if you took apart the rubber, if you will, on a basketball. However, if you're talking about how much could you stuff inside, that actually is going to be determined by the relationship between area and volume. If you were to take a calculus class, you would do something called integration and finding the derivative. The antiderivative is the integration piece. That would be the relationship between these 2 formulas, okay? And so if you do go on and you study that type of math, you're going to get to see the nice relationship. But for now, you have to take our word for it that you actually end up with 4 over 3, or 4/3, pi r cubed, pi r cubed. Okay, so again, if you know the radius of a sphere, you can calculate the surface area by squaring it, multiplying it by 4, and then times pi. If you want to find its volume, you need to cube the radius, multiply by 4, divide by 3, and then take that result and multiply it by pi. Okay, so that one you definitely want to have in your note cards because it's not as easy to remember. What about cylinders, though? In particular, we're going to talk about right circular cylinders. When I say right circular cylinders, I'm referring to a cylinder that is at a 90-degree angle with its circular base. So we have a circular base at the bottom here and at the top. So the radius is the same on the top as it is on the bottom, all right? And we also notice that the 90-degree angle means that this is not tilted over in any way, right? Think of like a can of soup, if you will. This would be an example of a right circular solid, right? 90 degrees at the circular base, okay, the connection point. So how would you calculate the volume of this prism? This is a type of prism, isn't it? Where you have the same surface at the top and the bottom at each of the bases. Well, the same idea of the original volume formula we talked about for prisms, where you take the area of the base times the height. Well, what is the base here? It's a circle. And what is the area of a circle? That's right, pi r squared. So the area of your base here is pi r squared. So that's what we see happening here. Take that area of your base and then simply multiply by its elevation or its height, and you have the volume that you can stuff inside. That's very important if you're talking about a can of soup, right? How much of my soup is in this can, right? And typically they'll measure that in ounces or in some type of units. But that's really important. If you're talking about medicine in a vial, you might be talking about cubic centimeters. So you're going to be talking about how much of maybe a liquid or a solid you can fit into your three-dimensional, in this case, cylinder, okay? So in that case, again, pi r squared represented the area of the base, and then we multiplied it by the height. Now, as far as the surface area formula is concerned, how much, in this case, aluminum, let's say, for your can of soup would be necessary to cover and to create the actual cylinder, okay? Well, you would need to have the area of the circular base on top, the area of the circular base at the bottom, and we know each of those areas was pi r squared. So if there's two of them, you have 2 pi r squared, 2 copies of that area. Then you would need to figure out how would I find the coverage around the body of the can of soup, right? Well, think about it, for example, if you ever opened your can of soup up and you notice that the label has wrapped itself around the can. If you disconnected that label and then opened it up, what type of shape would that label be in? If you said a rectangle, you would be correct, wouldn't it? So you'd actually get a rectangle if you looked at like your label that is in the body of this soup can, let's say. And you could calculate for a rectangle its area, couldn't you? You would need to have your base times your height, your length times your width. And in this case, to find the height, that's easy. That was already given to us as h, right? So that's the h part of the formula. But where does this 2 pi r come from? Well, do you remember that if you had a circle, which is really what would be required when you unwrap that label from your can, you'd have a circle that is wrapping around, right, on the top and the bottom. To measure around a circle, it's called the circumference of a circle. And do you remember what that formula was from our last video? That's right, it was 2 pi times the radius, or 2 pi r. Or you could just say pi times the diameter, since the radius is half the size of the diameter. So this right here, 2 pi r, that's the circumference of the circle. So when you actually spread that out, when you spread the label open, that would be our 2 pi r across, times your height from here to here, and 2 pi r times h gives you that piece of the formula. So that's where the surface area formula comes from for a right circular cylinder. Okay, so that would be its surface area. So make sure that you have those in your notes, you have them on a note card, and you understand what each piece means and how you would use the formula to get the answer that you need to solve the word problem, okay? Hey, let's head over to our next slide where we try to apply more of these formulas. So another formula that I want to take a look at is what happens to your prism if you actually don't have the same base at the top and the bottom, but you only have it at the bottom, and then at the top you hit at a certain vertex, if you will. Well, that's what we see here in the case of the pyramid and the cone, right? So in the case of the cone, for example, let's just talk about what we just had a moment ago. We were talking about the right circular cylinder, right, where we had the same base at the bottom and at the top, the circular base. Well, in this case, we don't have that base on top. Instead, we have a vertex that we are meeting up at. And it's a right circular cone in this case because we have a 90-degree angle. The cone's not tilting over in any way, okay? In this case, what you can actually do is check out the video that I've provided in the interactive notes online. There's a nice video that shows you that if you were to calculate how much liquid, in this case I think the video they use water, how much liquid is in the actual cylinder, the right circular cylinder, compared to this cone, you would end up seeing an interesting relationship. In fact, you could fit 3 cones into the cylinder. What does that mean then? Well, that would mean that each of the cones represents 1/3 the volume of the cylinder. So if you look back in your notes or look at the last slide, what was the volume of a right circular cone? It was pi r squared times the height, right? Area of the base times the height. So we took that pi r squared h and we multiply it by 1/3 because it's only 1/3 of the actual cylinder, okay? So that's pretty powerful right there. The volume of a cone is just 1/3 the volume of a cylinder, or 1/3 pi r squared h. Some people write it like this, pi r squared h, and then divide by 3. It means the same thing. Now, as far as, and that's the formula above here as well, as far as the pyramid, same thing happens. If you had a square pyramid, that's really the same thing as a square prism, where instead of having the square at the base and at the top, you're only going to have it at the base, and at the top you have a pointy vertex. Assuming that we have a right pyramid, so it's not tilted over in any way, the same thing applies, right? Area of my base, in this case, if it's square, that's b times b. If it was just a rectangle, that would be L times W, right? So that's the area of the base, so that's b squared in this case, times the height. That would give me the entire prism for a square prism. But now in this case, we notice, just like with the water experiment in the video that you can watch, for the cone that is actually 3 cones that fit into a cylinder, 3 pyramids fit into a prism, okay? So in this case, we're again going to get the volume is 1/3 of b squared h in this case. Or if it was a rectangular pyramid, it would be 1/3 of LWH. You could also write that as b squared h over 3, or just remember it as area of the base times the height divided by 3. Well, let's see if we can use these formulas in our example below. It says a cone has a height of 20 centimeters. Okay, so we have this situation above here. So our h is 20 centimeters. Its circular base has a diameter of 10 centimeters. So we're told d equals 10 centimeters. Can you find the volume? Okay, notice here we didn't talk about surface area. There are formulas for that, but for our class, we're not going to go into them. They're a little more complicated and use some skills that we don't quite have yet. So when we're talking about volume of a cone, we have a formula there. So if I were you, I would pause the video and see if I could get this right on my own. All right, let's see how you did. So for the volume of a cone, a right circular cone, remember the formula? It's 1/3 pi r squared, that's the area of the circular base, times its height. Okay, so we need to simply plug in what we have here and then use our technology to get an approximation. So our radius here is it given? Well, if our diameter is 10 centimeters, what does that imply about our radius? Remember that relationship? The radius is here, but the diameter is all the way from side to side, cutting through the center of a circle. So that would mean the radius is half of the diameter. So this would be 5 centimeters. So yeah, got to pay attention there. Don't plug in 10. So take your 5 centimeters, and if you plug in 5 and square it, 5 times 5 is what? 25. Nice job. So this turns out to be 25 in that part. So we have 1/3 pi times 25. And then we also have to multiply by the height, which in this case, they gave it to me as 20. So what I would probably recommend, if you have your technology here, what you'd want to first do typically is multiply the two numbers together, 25 times 20, and you'll get your answer there of 500, right? So you get your 500. Typically, you'll put pi at the end, and then divide by 3. So what you could do is you could go to your calculator. This is called the exact answer, by the way, 500 pi over 3. You could go to your calculator and you could type in exactly as you see it here, 500 pi divided by 3. Or you could take 500 divided by 3 and then multiply it by pi if you have a pi button. Most scientific and graphing calculators do. If not, you can use 3.14 as your approximation, but note you'll be a little bit off because you're rounding pretty early. When you do put this in your calculator, you should get roughly 523.6, I believe. Now, what would my units be? I rounded to the nearest tenth here. That's right, cubic units. So you could say centimeters cubed or cubic centimeters, right? Sometimes in medicine, you'll hear that known as cc's, cubic centimeters, same idea. Okay, so here we've given an example of how you can use the formulas to actually solve word problems, right? We haven't actually applied it too thoroughly yet, but you've seen a little bit of how you can find volume, how you can find surface area using the formulas. First step, recognition. What type of three-dimensional object or shape am I dealing with? Second step, what formula applies? And third step, can I plug these formulas in with the appropriate information that I'm presented with, and then can I understand and make sense of what I'm seeing, all right? So at this point, it's up to you to practice. If you have any questions, feel free to reach out to me, because remember, math is not a spectator sport. I will see you next time.